Modern AI models function as digital services, yet they rely on an enormous foundation of physical computing infrastructure. At a physical level, a foundation model consists of billions of mathematical parameters. These values are determined through trillions of matrix multiplication operations performed over massive datasets. To understand the current state of AI, we must look past the algorithms and examine the physical systems that make them possible. This infrastructure stack shows the dependency chain. It begins with raw materials and semiconductor design, moves through chip manufacturing and packaging, and scales into the servers and data centers hosted by cloud providers. The intelligence these models display is the specific result of a synchronized global pipeline involving semiconductor fabrication, high-speed networking, and large-scale energy management. Standard computer processors, or CPUs, are designed for serial logic operations, executing tasks one after another. Deep learning, however, requires massive parallel computation. GPUs contain thousands of smaller processing cores capable of executing many calculations simultaneously. This architecture allows them to perform the matrix multiplications required for AI training significantly faster than a CPU. Creating these chips involves a global supply chain. It begins with architectural design, followed by EDA software to verify transistor layouts. Next, specialized equipment etches circuits at the 3-nanometer scale. Foundries use these to fabricate wafers before final packaging. Because a single EUV lithography machine costs over $300 million and advanced foundries are limited to a few global locations, the capacity to produce frontier-grade AI chips is restricted by physical manufacturing availability. A GPU can only calculate matrix multiplications as fast as it receives data. This creates a high-pressure requirement for memory speed. In a standard memory hierarchy, traditional DRAM is often too slow to feed thousands of GPU cores at once. If the processor has to wait for data, its processing power is wasted. To bridge this gap, engineers developed high-bandwidth memory, or HBM. HBM consists of vertically stacked memory dies. By bonding these stacks directly to the same silicon package as the GPU, engineers reduce the physical distance data must travel, maximizing the available bandwidth. Advanced packaging that combines logic and memory is currently the absolute physical limit on the performance of an AI accelerator. A single AI chip cannot train a frontier model. To reach the necessary scale, thousands of these chips must be aggregated. An individual AI server integrates multiple GPUs with shared memory and high-speed network interfaces. This architecture allows a single server to handle massive workloads. Training a frontier model requires linking thousands of these servers into a cluster. This introduces a bottleneck, network communication speed. After every training step, the GPUs exchange model parameters across the network to ensure the cluster remains synchronized. This aggregation creates hyperscale facilities requiring hundreds of megawatts of power, comparable to a small city. Advanced liquid cooling systems manage the intense heat. Without high-speed interconnects like InfiniBand, these billion-dollar clusters fail to scale, as the GPUs spend more time waiting for data than they do performing calculations. Once the physical infrastructure is in place, it is fed with petabytes of training data, ranging from scientific literature to computer code. This raw data must undergo a rigorous processing pipeline. It is filtered for quality, deduplicated, and finally broken down into machine-readable units called tokens. To process these tokens, researchers use a software architecture designed to maximize the parallel processing capabilities of the GPU clusters. In this transformer flow, tokens are converted into vectors called embeddings. These are then processed by a self-attention layer. Self-attention allows the model to calculate relationships between all tokens simultaneously. This mathematically intense process relies entirely on the parallel hardware we have built. The stack exists entirely to support this training process. The optimization loop repeatedly predicts the next token, calculates error, and updates parameters. This is parallelized across thousands of accelerators. Each GPU computes a portion, synchronizing across the entire cluster. Distributed training runs continuously for weeks or months. This massive mathematical operation requires a constant city-scale power supply and an ultra-fast network to keep the thousands of processors in sync. The production of AI-generated tokens is restricted by physical manufacturing availability, the thermal limits of silicon, and networking latency. Foundation models are the physical result of optimizing billions of parameters over trillions of tokens. They are made possible only through the integration of semiconductor manufacturing, specialized packaging, and hyperscale data centers.